This is Jack Jackson back, this time with the law of sines. In our last video, we derived the law of cosines, which we saw was an extension of the Pythagorean theorem, and it allowed us to solve triangles, or at least get started on solving triangles, in the side-side-side case and the side-angle-side case. Well, what if we're not in one of those cases? We're going to derive another result called the law of sines, which you see here. Sine A over side A equals sine B over side B equals sine of angle C over side C with our standard labeling. And so basically this is sort of generalizes or makes more specific, I guess I should say, something we noticed earlier, that the bigger the angle is, the bigger the opposite side is. At least, and so we get some kind of proportionality relationship here that you see here in this result. So let's prove it. Okay, so we start with any triangle ABC, and say here it is. Can be any triangle we want. And as usual, we're going to let the uppercase letters A, B, and C stand not only for the vertices, but also for the measures of the internal angles at those vertices. And little b, and little c are the lengths of the sides opposite. So little a is the length of side opposite angle A, so that's the length BC. Little c, lowercase c, is the length of the side opposite angle C, so that's the length from A to B. And similarly, B is the length of the side opposite B, so that's AC. In other words, our standard notation. And we're going to take the line AB and draw up a perpendicular to it from C, which would be our altitude. From A, perpendicular to BC. That's a typo. This should say BC. Let's fix that. There we go. From A to BC, and we'll call this point D. Now, this point D might be outside the triangle, it might be inside the triangle, it might be a side of the triangle. Could be either way. Now, let's take a look at this and see. Let's look at the sine of angle B. Sine of angle B is H over C, as we can see from this picture. If we're over here, the sine of, well, let's look at the options here. Let's okay. When you're in this situation, angle B is an acute angle. Okay, and angle B is an obtuse angle, but this angle over here at B is an acute angle, but both of them have the same sign. Remember, supplementary angles have the same, the sign of the complementary angles is the same. So in either way, the sign of this angle, big angle B, obtuse angle, is still the sign of the smaller angle at B, which is H over C. In the case that it's here, the sine of angle B is 90 degrees, or pi over 2 is the angle, and the sine it's H over H, which is 1, and the sine of a 90 degree angle is 1. And if you're over here, then we're looking at this little triangle, and we see that the sine of angle B is opposite over hypotenuse, so it's H over C. So in all three cases, whether you're here, here, or here, we do get this case that the sine of angle B is H over C. Similarly, we're going to get the sine of angle C is H over B. Similarly, again, we could have the possibilities here. Looking at this triangle, if we have an acute angle at angle C, that's opposite over hypotenuse. That would be H over C for that right triangle right there. Of course, if it is a right angle right at C, then H and B are identical, they're the same length, and we get, well, H over B is 1, and the sine of a 90 degree angle, or pi over 2 angle, is 1. And once again, when we have an obtuse angle at C right here, we see that it has the same sign as this supplementary angle here, and the sine of this angle from this triangle ADC is h over b. So either way you go, any way you go, I'm going to put it back to this picture here, but it doesn't really matter. In any case, sine of angle B is h over c, and sine of angle C is h over b. Now it's the same h in every case, so let's solve for h. H is c times sine of b, and h is b times sine of c, so those are equal to each other. So c times sine of angle b is side b times sine of angle c. And so just get the c's together, the b's together, divide both sides by b and c, or multiply both sides of the equation by 1 over bc, and we get this situation here. Sine of angle b equals sine of angle c over c. And so in fact these last two fractions are equal. And in a similar manner, we can have another altitude from C to side AB. And this time, let's hide this other one. And in a similar manner, we're going to do the same thing. So this time the sine of angle B is H2, we could call it here, the red one, over hypotenuse, which is A. And again, it's going to be, it doesn't matter whether this is here, 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 same reasons as before. It's still always, let you look at that for a second if you need to, and then here, and here. And in each case, we get that is H2 over A. And similarly, the sine of angle A, here's angle A right here, same as the sine of here, so it's H2 over B, or if we have it like this, H2 over B. So either way you go, we get, no matter how this lines up, we get the sine of angle A is H2 over B, sine of angle B is H2 over A. Solve for H2, so we multiply by A here and by B here. And they're equal to each other because they're both equal to H2. Divide both sides by AB, and you get sine of angle B equals sine of angle B over B is sine angle A over A. So we get sine of angle A over A, side A, is equal to sine of angle B over side B, which is equal to sine of angle C over side C. So if we take any two of these fractions, and we know three of the parts, then we can solve for the fourth part. Okay, so in particular, notice that requires that you have one fraction completely done. So for example, if we only knew the little a, b, and c, this wouldn't be enough, because when we put two of the fractions equal to each other, say the first two, we would have two unknowns in the top. Okay? So, but if we have an entire fraction done, like we know both an angle A and the opposite side A, and then if we know either little b or big B, we can solve for the other one. Okay? So, notice that you can use the law of sines when you know an angle and a side opposite it. Okay? So, let's go back here and hide a few things. And so let's talk about how we might use the law of sines. So if the length, notice that we know the length of the side and the measure of the opposite angle. So we know one of those entire fractions. Then we know one other measurement, then we can solve for at least one missing measurement. So this will be the starting point when we have either the AAS or SSA information given. So in the AAS situation, notice we know this angle and this side are both known. So for example, if we're solving for side B, when we know angle A and angle B and side A. So we know both angle A and side A, so we know little a over sine A is little b over sine B, but then multiply both sides by sine of B, and we solve for B. So there's an example. And of course, you can use a similar example to solve for any situation in the angle-angle-side situation. Now what if we start with the angle-side-angle situation? What we can use is the angle sum theorem. A plus b plus c equals pi radians, or 180 degrees. Use that to find the third angle, and now we're back in the angle-angle-side position, because then we will have an angle and a side opposite each other that's known, and we can solve for one of the missing sides. Finally, you can solve for the final side then using either law of sines or law of cosines. Now, you have to be a little careful when you're using law of sines to solve for an angle, okay? When you're solving for a side, law of sines is straightforward and perhaps maybe even easier than law of cosines when you are given a choice. Sometimes once you get going in solving a triangle, once you have 4 pieces of information or 5 and you're looking for that last 2 or 1 piece of information, then you have further, you have multiple ways of going at it. So you might be able to use law of sines or law of cosines or the angle sum theorem. You may have several different multiple ways of going at it. But in the angle side angle, or side angle conditions, you have to start with the law of sines. So if you're using law of sines to find an angle, you should be very careful. So I will prefer to use the law of cosines to find an angle when we actually know or we have figured out all 3 sides. But in the side angle condition, you don't have a choice. You have to solve for the angle using the law of sines. So here if we have, maybe I should show you this setup. So if we're solving for, so we have cosine of angle B over B equals a cosine of angle A over A. And if we're trying to solve for angle B, we start by multiplying both sides by the length of side B. And then, so we're down to this situation. Oops, that's supposed to be sines. Excuse me. This is the law of sines, and these are sines here. Now, when we try to go from here, and we have the angle B. Now, angle B has to be a measure of an angle that's actually in a triangle. So that's between 0 and pi radians, or 0 and 180 degrees. But the problem is, so if this expression here should be some kind of a positive expression, okay, because angle A is an angle that's between 0 and pi, so the sign will be positive, and these are side lengths, so they're positive. But so the output, though, if I just did arc sine of this, like this, that's going to give me an acute angle. But the angle might be obtuse. So you have to also say, what's the other possibility? B might be pi minus that, using radians here. So there are 2 possibilities. This is an acute angle, this is an obtuse angle. Now, you have to then go from the context of the problem to see if there's some reason we might be able to eliminate one of these. Okay, so for example, if this angle A is already an obtuse or a right angle, we know that the obtuse version here is not going to be allowed. But other cases, that actually both of them do work. And as we know, the side angle condition, it does include that ambiguous case where there are 2 different solutions, and this is how you get them. This will be one angle here, this will be another angle, and we get 2 complete solutions. In other cases, for example, the big S, the less A condition, one of these will work, but the other one will at some point reach some kind of a contradiction. So we have to be careful that there are 2 different possibilities there for the law of sines. So, when we put this together with the law of sines and the law of cosines and the angle sum theorem, we have 3 results that can be used with any triangle, and we can use those results to help us solve those triangles.